Through 5 years of FTC, most of it with very poor CAD skills, like you don't want to know. One of the big questions on my mind while looking at good robots was just how do they design that stuff? And it's a very broad question, and there isn't really any way to succinctly answer it at all. This video is a long-winded answer, but it's the best I can give without literally having you sit next to me while I attempt to CAD a robot. Now, if you're still watching, cool, let's get into it. So, before we talk about CAD, let's just go over my design requirements for this robot. My goal with the robot was to design something that can make a good run at states in almost any region while being as simple and easy to execute as possible. I obviously had the benefit of hindsight with this, given that I made this very late in the season, and this video probably isn't coming out until after Worlds. In most years, having a robot that is made in large part with off-the-shelf parts is fine, and I'd argue that it's a good idea for many teams. But a shooter game makes this more difficult, especially given that the artifacts are so big relative to the size of robots. As a result, I decided that the robot would be built out of 1/8-inch plates, which could be laser-cut plywood for prototyping and aluminum for the competition-ready robot. I'm still using a fair amount of off-the-shelf parts. You aren't going to be seeing any custom cross-bracinger here because, to be honest, I'm not interested in saving grams. But this robot does require both 3D printing and some kind of machining or laser cutting, which I still think is reasonable scope, especially with the existence of services like FabWorks and SendCutSend. This is the stuff that I had decided before even opening any CAD software, so now let's get into the CAD. Let's start out with the master sketch. I used to call this a layout sketch, and if you look on my channel, one of the videos is called layout sketch. But I've realized that calling it layout sketch makes it sound more like a suggestion and less like a requirement. So master sketch it is. So firstly, I'm using Origin Cube. As you will watch, as you will see, it's awesome. Like genuinely, why would you not use Origin Cube? Come on. So anyway, get Origin Cube. Please use it. Not actually for the Origin Cube, but because it has some really nice feature scripts in it, especially with belt center-to-center distance calculation. You'll see what I mean later on. But the other thing, I started out with just the sizing limits along with a game element for my master sketch. If this were a pick and place game, I would also probably put in the scoring objective. Like if the basket is of a certain height, I would have that basket in there in CAD. But that isn't really applicable for a shooter game. Now, a very cursory top view is usually useful just to define the horizontal dimensions of the robot. This will drive some of the rest of the sketches in the Master Sketch Part Studio, but won't actually contain much information or do too much. For most robots, the side view is the most critical group of sketches. Usually, I would make a primary side view sketch that defines the path of the game elements along with rough placement of mechanisms, pivot points, etc., and then have more specific sketches for each mechanism that define what it will do with the game element and how exactly it will function. And just to be clear, I mean that everything possible is driven. Again, the master sketch is law, not suggestion. As a forcing function, you could try to avoid sketch dimensions as much as possible, as that'll make you constrain things in new sketches to that of old sketches. So the outline side sketch that you make, all of your future sketches in that plane should be based off of your initial general sketch. And you should try to use as few external dimensions as possible. Now, a few tools. Again, the Origin Cube functions are really nice for this because they automatically calculate the correct center-to-center distances, which is better for showing design intent than having to use external calculators, and then copy in a seemingly random number. My shooter also involved a GT2 belt run. I derived a center-to-center distance sketch from a document in Lunilib, which you will see, and used a measured variable to get the correct distance into my sketches. I spent really long on this, and it's not by accident. It is much easier to find and fix problems in a master sketch than after you've already CAD'd a bunch of stuff, just because in a master sketch you are working with a couple of sketches, whereas once you CAD entire parts, then you have to worry about the whole flow from the sketches through the extrudes and whatnot and so on, right? So the sooner you catch your problems, the better off you'll be in the long run. Finally, as for the specific design decisions, I'll hit on them as we go through the mechanisms, but here are some of the major things you should take into consideration while making the master sketch, beyond just the mechanisms themselves. So, one of some of the things are the game elements and their path through the robot, the control and expansion hubs, and also if you're using like a servo hub or something like that, that should also definitely be in there. The battery, oh my gosh, you have there are a ridiculous number of pre-built robots with really, really bad battery placement. If you are CADing your robot, that is a massive thing you have to keep track of is where are you going to put your battery. Same thing with motors. Motors are big, especially for FTC. They're really big relative to the size of the robot itself. So make sure you include your motors in your master sketch. Sometimes your servos, depending on how packaging works. If you're making a layout sketch, a master sketch for something that's in like a very constricted area, then you should definitely have your servos in there. If you know and you're very confident that you're going to have space, then maybe you don't have your servos. So that's kind of up to you and up to the situation that you are in. And some of the later things, robot signs. This is very subtle foreshadowing for what happens later. And sensors, especially odometry, because since it requires area near the ground, it can become difficult to package later on. So make sure you get your odometry in your master sketch so that way you don't have to worry about it later. And one of the other things is just general wiring. This is something that's often neglected, and then wiring, especially with mechanisms that move like turrets or linear extensions, wiring can become a real pain later, so it's better to take care of it in CAD, or at least leave room for yourself to work on it physically, right? Now, before going through the mechanisms, it's time to point out what I did quite poorly here, and it kind of starts off straight away. I didn't use version control or a multi-document system. I would like to endorse the FRC design method for organizing robot CAD. As you'll see, what I did technically works, but there was an unholy amount of lag in the drivetrain and main assemblies, and it would also have been very difficult for anyone else to work on the CAD with me. If I went through all of the version control and organization best practices right now, that would be an entire video in and of itself, and this video is already going to run long enough as is. So check out the FRC design website. The people there have already done all of that, so go check it out. Link is in the description. Keep in mind though that their setup is targeted at FRC, so you may need to modify some things to work with your workflow and with FTC components. So now, back to what I actually did. Let's first talk about the drivetrain. The master sketch already defined a parallel plate drivetrain because it is the meta for a reason, right? Given my goals with the robot design, there was no point in making the drivetrain more complicated than it needed to be. So it was fairly cut and dry. The only thing that took some complexity was figuring out the motor mounting plates standoff arrangement, because I was kind of trying to make things a little bit short. It's not really that compact by modern FTC standards, but it took a little while. The hubs were mounted to the inside plate of the drivetrain facing outwards to make wiring easier, etc., etc. There are a whole bunch of like minute things that you probably wouldn't notice unless you actually tried to make the drivetrain yourself. There is one thing that you probably notice is weird about the inner plates, and that's these holes on the inside. Basically, while making the master sketch, I realized that if I were to make the shooter, drivetrain, and intake plates be the same plate, it would be slightly more compact, but way harder to iterate on, because every time you wanted to change a subsystem, you would have to take apart the entire robot to do it. So instead, they are all modular systems, and the master sketch ensures that the mounting holes that will connect them will all be in the same place relative to each of the mechanisms. As for some of the different tools I used, and you will see that many of these will be repeated, the hole tool in Part Studio, it's way faster and more parametric than having to manually draw out each screw hole. Also, the replicate tool in assembly is kind of the same intent as the hole tool. It makes screw and standoff mating much less painful. And finally, the last one I want to talk about with the drivetrain, although I did use other things too, but the mirror tool in assemblies. It also exists in Part Studios, but the assembly mirror is like the Onshape community in general has been waiting for this for years, and we finally got it sometime last year. So we don't have to manually make each side of the drivetrain now. We can just make one side and then mirror it over to the other side. Now, my main mistake with the drivetrain, if you can call it that, was not putting in all the screws. So I kind of just got lazy and didn't put all the screws in on both sides everywhere that was necessary. Again, I am a washed alumnus, so that should explain for you. But the other funny thing I did was use some 1032 button head screws for mounting the wedges. I'd have to thread the screw beams, I don't know, whatever, the hole beams, I don't know what you call them, but I would have to thread the holes to 1032 for this to work, but at the time it seemed like a simpler solution than having some kind of other attachment method, especially because I didn't want to deal with nuts on the other side of the square beams, just for packaging reasons. Moving on to the shooter now, this involves some of the more complex 3D printed parts of any of the mechanisms on this robot. Between the adjustable hood gears, the servo mount, etc. Again, all of this was parametric. I don't think I was even typing in the number of teeth for each gear. I just had some measured variables and stuff. So all of this, the goal was basically use as much information as possible from the master sketch so that if I need to make changes to the mechanism, I can simply change the values in the master sketch and everything will flow down and change how the shooter looks as well. Some of the interesting points were, I guess, the shooter drives the wheel with a GT2 belt, as I mentioned earlier. GT2 belts are kind of notorious for stretching, at least the ones that you get on Amazon. I made an adjustable tensioner that will allow for the change in belt tension with just the loosening and tightening of a few screws. Some attention also had to be paid to make sure that the balls were centered in the shooter before they touched the actual shooter wheels. So I have this 3D printed transfer ramp to hopefully center the balls so that they go in nicely aligned. And finally, the flap that stops balls from accidentally being fed into the shooter. It was one of the things that I didn't put in the master sketch. This is, in my opinion, an example of when you don't need to put servos in your master sketch, because I was just really confident I would have space for it, because it wasn't really near any of the other things on the robot. And somehow that actually worked out that way, so that was cool. I just built it within the shooter parts document. It's not entirely parametric, but honestly, it just kind of saves time. The big sus thing that I'm concerned about with the shooter is the idler gears between the two shooter motors. It's aluminum, while the motor gears are steel, and it is also dead axled to a standoff that has one end attached to the shooter plate and the other end attached to a drivetrain plate. This seems like potentially a recipe for extremely fast gear wear, so definitely something to be prototyped and tested. Now, for the funniest part of the robot, in my opinion, the intake and the transfer. This is kind of a series of strange design decisions that may or may not work. Most of them were avoidable, but again, I am a washed alumnus. So it seemed like too much work, and I just wanted to minimize the number of degrees of freedom as much as possible, while maintaining contact with the ball at all times. In speed we trust is fun and all, but I really didn't want to take any chances. So, for some of the specific design decisions that were made, fixed compression in the intake. So a lot of robots in Decode, including one of my team's robots, had variable compression intake. So the intake is on a slap down or something like that. It's on a pivot so that it can press down and accommodate the ball at various heights. But I thought that if I could just prototype to figure out the exact correct compression necessary, I wouldn't need to worry about that. And so for that, I used kind of moderate compression, but also with squishy wheels, so that I have some more freedom with that. The other thing was intake bias, so I had different wheels on either side, which coincide with the slight differences in drivetrain wedges to bias the intake towards one side or the other. So that is just to make sure that if the ball has to intake 3 walls from up against a wall, it will do so efficiently. Now, one of the other things was different transfer wheels or flaps. So I used Optake, which is the the funny 3D printed thing with like little tubes attached on the end. So I use that along with some geckos for the first transfer roller. That's another thing that needs prototyping because Optic just kind of behaves very differently based on the type of tubing you use. So definitely something that needs to be tested. Now, the last thing I want to point out is that I used a round belt to power the second transfer roller. This is not normal for me at all. I'm a firm believer in positive drive, but I wanted this roller to be able to stall out even while the intake and other transfer roller were spinning. And round belt seemed like a very simple way to achieve that. So that's what that was. And again, all of these things need to be prototyped because I made a lot of assumptions with this design. And if I were making this during the season, this would all be 3D printed and laser cut and built out of relatively affordable materials, and just testing the concepts before I actually would even consider making this out of aluminum and so on. As for some of the foreseeable problems, I don't know if having only 2 transfer rollers will be enough, especially because the first one uses really big optic flaps, and the reason it uses big optic flaps is because it needs to be able to move the balls, like have reach over the balls for a very large distance. But I don't know if that's going to work. So again, prototyping is very important. And finally, current draw. Getting the round belt to slip will require torque, so current draw will probably get funny. Thing is, I don't know enough about current management to actually do anything about it in design. So if needed, maybe we could switch the round belt out for rubber bands or something that is thinner and therefore easier to stretch and will require less torque in order to make slip. But again, this is something, again, prototyping is important. I'm probably going to say this a lot. This also seems like a good time to point out something that I think I was doing well, organizing features and parts into folders and having descriptive names. For the love of all that is good about your teammates, do not leave features, mates, parts, especially in part studios, as a giant list that other people have to sort through. It is true pain. And if they need to make a change, they may literally just delete and redo everything you spent your time on because it is too hard for them to find that one feature they need to edit. So, I am saying this from experience. Please organize your stuff. Now, after doing some configurable pocketing, which could be enabled or disabled depending on what type of material I was manufacturing stuff out of, and then also assigning materials, and colors and attaching everything, all the subsystems with the steel plates in the main assembly, I thought I was done. Then I went back and spent another 2 hours color coordinating spacers, making tiny adjustments, and making the robot signs I had forgotten about earlier. Most of this time was really spent waiting for stuff to load, because again, I really messed up on document structure and version control, and it bit me in the end. So, again, make sure you manage that stuff properly because lag is not fun, especially because a lot of you probably don't have really beefy computers. And if you have a beefy computer, it's possible that your teammates don't. So make sure that everyone has good access to CAD, and part of that means you make stuff actually runnable on their machines. At this point, it occurred to me that as I was trying to provide a good example of going about designing an FTC robot, I should get my CAD reviewed. CAD reviews are really important, and if you know anyone who understands robots and did not actively work on designing yours, you should ask them to review your CAD. If you work on CAD for long enough, you will end up getting tunnel vision. It's going to happen, and it does not behoove you to be running around online spending hundreds or thousands of dollars on a robot that is inherently flawed because you were wearing horse blinders. I asked an Apple to review my robot CAD. And here's what it said. I should ensure that the screws connecting the subassemblies or subsystems are accessible. I should change the geometry of the funnels to be more asymmetrical. I should figure out wire routing between the control and expansion hubs. And I should use a plate to mount the hood servo instead of having it just be attached with a bunch of standoffs. Again, because I am a washed alumnus, I didn't implement all the changes it suggested, but I did change the funnel geometry and use a plate to mount the hood servos. If I was actually planning to make this robot in real life, I would probably put more effort into optimizing the wiring, because it would probably work with this design, but it wouldn't be very convenient. Either way, thank you, Apple. And that brings us to the present. I hope you've learned something. If you want to watch the full recording, link is in the description.